And now we're going to do continuous probability. And on the continuous probability, we're only going to talk about three in particular. One is the uniform, one is the normal distribution, and one is the exponential distribution. Now each one of these has a relationship with one of the discrete distributions. The uniform clearly goes with the other uniform distribution. The normal distribution is actually an approximation of the binomial distribution. If you were to take it out, it would be really, really big. And then the exponential distribution is closely related to the Poisson distribution. Hypergeometric doesn't have a continuous version. Now one thing I want you to see from this picture here is that they all look pretty different, and that I've actually shaded the area that's underneath the curve. Notice that all these parts down here are shaded. One thing that's going to be different between the continuous random variables and the discrete random variables is that the discrete random variables, each observation has some probability to it. Meaning x equaling 0 has some probability to it. X equaling 1 has some probability equaling to it. Here, in the case of a continuous random variable, they do not. The probability of any one element is exactly equal to 0. And the reason is that in the case of a discrete, you can think that there was some probability mass underneath them. Kind of like they were sitting on top of a pedestal. Here, the pedestal gets cut up so finite, because there's a continuous number right next to it, that there is no mass sitting underneath that number. It's cut up so much that it's basically 0. Which means that we can only really talk about spaces between values. And the way we do spaces between values is that we look at the area in between those 2 points. In the case of the uniform, it's actually quite easy. Right, you have a lower bound, you have an upper bound. Given a particular x, you just calculate the area of the rectangle, and that gives you the probability. In the case of the exponential, there is a formula that you can use, and I'll show you what that formula is, to calculate the area underneath the exponential. In the case of normal distribution, we don't have any of those. We have to actually use a table or a very good computer in order to do that. And so you will notice that if you've taken this class before, or if you looked at my formula sheet, I have this big table in there for the normal distribution. That's what we use, because there is no closed form solution for the normal distribution. So instead we have to use computers to approximate this area. So a continuous random variable can assume any value in an interval on the real line or in a collection of intervals. The reason we say collection of intervals is that maybe I want to ask a question like, if GPAs are continuously distributed, what is the probability of having a GPA that is greater than 3.0 or less than 1.0? Those are two different intervals. You should still be able to calculate those two probabilities and add them together. It is not possible to talk about the probability of a random variable assuming a particular value. Again, there's no mass underneath that 1 point. 1.0 is very close to 1.001 and very close to 0.99998. How do I know that I'm attributing the right probability to one or the other? I can only talk about distances between the two. So instead, we only talk about probability of the random variable assuming a value within a given interval. So for continuous random variables, we're going to be using the cumulative distribution quite a lot. There are functions for the probability density function. So just the, if you will, the straight probability like we used back in the discrete form, but they are useless by themselves. And they will produce a number. So if you put in a value into there, it's still a function. It'll spit a value back out, but that value is meaningless. Alright, so here's the intuition. Assume for a moment that the random variable takes on a different value, and each value has an equal probability of just 1 over n. So straight uniform. Straight uniform, every value has a probability of exactly 1 over n. Problem is, I told you that it was continuous, right? So what is n equal to? Infinity. So 1 over infinity equals to what? 0. So there's no probability mass on any one point. So the probability of random variable, assuming a value within some given interval from x1 to x2, is defined by the area underneath the graph of the probability density function between x1 and x2. Now these probability density functions, they exist. And if you plug a number into them, they'll spit a number back out, but that number is not the probability of x1 or x2. Instead, they tell us if we integrate over them the distance between 2 points. Is anyone taking calculus in here, or relevance of calculus? Alright. And so, the distance the area underneath the curve is done by the integral, right? So what we're doing is we're taking this probability density function, and we're integrating it between the two endpoints. And that tells us the area underneath the curve. So that also tells us the probability. Now, I'm not going to go into any details about that because this prerequisite for this class was not calculus. So you just have to take it on my word. So for those of you who have had calculus, that's what we're doing. We're looking at the area underneath the curve. And we can always do that with integration. For the case of the uniform, we can do that with just straight algebra, right? Length times width, we can find it. But for normal and for exponential, we can't. Alright, so we have random variable that's uniformly distributed whenever the probability is proportional to its length, meaning that every observation, in theory, has an equal probability of occurring. There is no central tendency, if you will. The uniform density function is actually just quite flat. You take 1 over the highest value minus the lowest value. Notice that x is nowhere in there. So this really is just a rectangle. This is telling you the height of that rectangle. And you're going to give it two endpoints. So the probability density function is, of course, useless in this continuous random variable, but we can still use it to find the correct height and then get the cumulative distribution. So the cumulative density function works exactly as you hear it. It adds up all the probability between 2 points, and it answers the question, what is the probability of being equal to x or less than x? So including x. All the values are equal to x or less than x. For the case of the uniform, the cumulative density function is very simple. You take the observed value of x, and you divide it by b minus a. X can only exist between b minus a. Any value of x that is greater than b says that we're covering the entire distribution. So there it has to equal 1. And any value of x that's less than a says you're outside the distribution, so it has to be equal to 0. So the expected value of a uniform distribution is actually quite simple. You take two endpoints, add them together, divide by 2. Why? Well, every point is equally likely, right? If every point is equally likely, then it's just like taking any other average. Variance is a little odd. You can prove this to yourself using calculus. I'm not going to do that in this class, so for right now, you just take my word at it. But it's equal to b minus a squared divided by 12. 12 is generated by the calculus. Other than that, it has no other meaning. So similar to the binomial distribution, it has a very simple formula for its mean and for its variance. You don't need to go through a series of squaring things. You can just plug in the two endpoints, and you can get your variance, and you can get your mean. Here's one example. Slater customers are charged for the amount of salad they take. Sampling suggests that the amount of salad taken is uniformly distributed between 5 ounces and 15 ounces. So in other words, our endpoints here are going to be 15 for B and 5 for A. Since that's true, our density function has to be 1 over 10. That's 1 over B minus A. And X is going to be the amount of salad taken. So then the expected amount of salad taken is going to be the sum of those two endpoints divided by 2, which is just 10. And the variance is going to be 15 minus 5, which is 10. We square that, which gives us 100, and then we divide 100 by 12, which gives us 8.33. Alright, so the uniform should be pretty plug and chug. Just practice it, and you should be able to use it without much trouble. Alright, there's our distribution. Again, pretty boring, just a rectangle on the side. So now the question is, well, what is the likelihood of finding that someone takes 12 to 15 ounces of salad? And there are two ways you can answer this question. One way is to find the probability they take 12 ounces, find the probability they take 15 ounces, and subtract the 2. Right. Or just notice that 15 is the top, and take the probability of taking 12 ounces or less and subtract that from 1. So what we're doing is we're saying probability that X is in between 12 and 15 is equal to f of x equaling 15 minus f of x being less than or equal to 12. Now whenever I use the big F like this, I'm always talking, whenever I use that lowercase f, I'm talking about probability density. That's the one that, in the continuous case, doesn't really help. So in our example here for 15 and 12, this is going to be 15 over 15 minus 5 minus 12 over 15 minus 5, which is going to give us 3 over 10, or 3/10. Now we're showing you this rule with the uniform because it's pretty intuitive, right? We're using the same rules for all the other distributions. We want to know what is the likelihood that x falls between 2 points. We have to take the CDF of the top point minus the CDF of the bottom point. Now this f function will change with each distribution, but the rules are always the same. All right, the area under the graph of f of x and the probability are identical. This is valid for all continuous random variables. And the probability that x takes on a value between some lower value of x1 and some higher value of x2 can be found by computing the area underneath the graph. For the case of the uniform and the exponential, I give you a nice closed form solution for that function. For the case of the normal distribution, you've got to do a little extra work. So here's the normal. We're going to talk about the normal a lot in this class. Right. We're going to do a little bit of it today. We're going to do a lot more of it tomorrow. We're going to use the normal distribution quite a lot. So we want to become very familiar with the tables we're going to be using. Now, normal distribution is that bell-shaped curve. It's widely used in statistics. It's been included in a lot of applications. The height of people, rainfall amounts, test scores, scientific measures. And it was made up by a French mathematician. And what he did is he recognized that a lot of things in nature follow this bell curve. Alright, so now this is the probability density function for a normal distribution. It's quite ugly. Of course, just trying to integrate that would make it even harder. And you can try. If you find an answer, the world will be very much obliged. But there is no closed form to this particular distribution. You can see that you can plug in a number here for x, and it'll spit a number back out to you, but it doesn't mean anything. Right, what we need to do is we need to integrate this. Now, a normally distributed random variable can take any value between negative infinity and positive infinity. So the lower bound here would be minus infinity. You'd have to start there. And you'd have to integrate all the way up to x. Right? That's not fun. So what we need to do instead is find a different way to represent this problem. What we're going to do is we're going to exploit some of the rules we learned before, like the Chebyshev rule, and that z-score, the deviation from the mean. We're going to use that to try to get us around this problem. All right, some characteristics about normal distribution. It is symmetric, meaning it has no skewness to it. Its mean, median, mode are exactly in the center. You can go ahead and fold it on itself, and it should line up perfectly. The entire family of normal distributions are defined by its mean and its standard deviation. Those are the only two parameters you need to know. So we're going to use that fact. We're going to use that fact because it means we can take any normally distributed variable and make it into a standard normal. We'll talk about what a standard normal is in a second. But we can take any normally distributed variable and convert it into one type of normally distributed variable. What I mean by that is we can have one variable that has a mean of 10 and a standard deviation of 2. We have another one that has a mean of 2 and a standard deviation of 0.05. We can collapse both of those two types of variables into one type. That way we only have to learn one table. The highest point of the normal curve is at its mean. That's where its median's at. That's where its mode's at. The mean can be any numerical value, both positive and negative. It includes 0. So it's not restricted like some of the discrete distributions we had. It's not restricted like the uniform distribution where it has to have a lower bound, it has to have an upper bound to it. The standard deviation determines the width of the curve. Larger values result in a flatter distribution. Smaller values result in a tighter distribution. And this should make sense, right? If the standard deviation is getting bigger, that means you have a larger variance, right? We're always taking the square root of the variance in order to get to the standard deviation. So if the standard deviation is getting bigger, the variance has to be getting bigger. And if the variance is getting bigger, it means that your values of x are moving along a lot more. Alright, so the probability of the normal randomly variable by the area underneath the curve is exactly split into 0.5. So you have 0.5 on the left-hand side and 0.5 on the right-hand side. Which means that if I had a cumulative density function and I asked you, what is the likelihood of being above the mean? You could answer that without doing any work, right? Or what is the likelihood of being below the mean? Again, you do that without doing any work. It has to be exactly equal to 0.5. Now this is the reason we use this. The normal distribution follows the empirical rule very closely. 68.26% of the values are found within one standard deviation of the mean. Within 2 standard deviations of the mean, we have about 95.44% of all of the data fall within there. And then within 3 standard deviations of the mean, we have 99.72% of the data falling within that range. Why is that important? It means that we don't really have to care about negative infinity or positive infinity. Right? The likelihood of those events are so small, as if they're not even there. They're so tiny, we shouldn't have to worry about that. So the way you find those areas is that you take your mean, and you add 1 standard deviation to that mean, and you subtract 1 standard deviation to that mean. That gives you an interval. Within that interval is going to be that first 68%. You do it again for 2 standard deviations away from the mean. Again, within that interval, you're going to have 95% of your data. You can do it again for 3 standard deviations away from the mean. Within that interval, you have 99.72% of the data. And this is going to be true for all normally distributed random variables. So a random variable having a normal distribution with a mean of 0 and a standard deviation of 1 is called a standard normal distribution. This is the distribution we're going to learn the most about, because we're going to be able to take any other normally distributed random variable and turn it into a standard normal. Alright, so we can take any other normally distributed random variable and convert it into a standard normal. So we only have to learn the probabilities for a standard normal. So any normally distributed variable can be transformed to the standard normal. And the way we do that is with the z transformation. Hopefully you've already done the z transformation at least once, right? It was probably part of your homework assignment, chapter 3. Now the way we do that is that we take our x, we subtract off the mean, and we divide through by the standard deviation. Let's think about why this works. Here's my normal distribution. Here's mu sitting in the center. Here's mu minus 1 standard deviation. Here's mu plus 1 standard deviation. Right? Okay, the first thing I do is subtract mu from everything, which is what this step says, right? Take all the values of x and subtract it by mu. All I'm going to do is put this now in its center. That's the first step to making it into a standard normal. It has to have a mean of 0, right? So all I'm doing is subtracting the mean, the mu, from all values of x. Now that hasn't completely fixed the problem because I still have this standard deviation running around. So the next thing I'm going to do is divide everything by the standard deviation. If I do that, now those same measures become units of standard deviations, meaning standard deviation is exactly equal to 1. So I can take any normal random variable and convert it into a standard normal. That's the reason we use normal distribution. It's not true with the exponential. It's not true with the uniform. But with the normal distribution, it's always true. So these same distances, these same characteristics that we see here for the normal distribution, hold for the standard normal. Meaning that within 1 standard deviation, where this is equal to 1, it's still 68%. When this is 2, it's still 95%. When this is 3, it's still 99%. Alright, so here's one example. Pepzone sells auto parts and supplies include a popular multi-grade motor oil. When the stock of the oil drops to 20 gallons, a replenish order is placed in. The store manager is concerned that the sales are being lost due to stockouts while waiting for the replenishment order. It has been determined that demand during replenishment lead time is normally distributed with a mean of 15 and a standard deviation of 6. The manager would like to know the probability of a stock out during the replenishment lead time. In other words, what is the probability that demand during this lead time will exceed 20 gallons? So you know the mean, mu here is 15. You know the standard deviation is 6. And you know that what you want to know is whether or not x is going to be greater than 20. What we need to do is take this as our x, apply it to the z-score, and then we got to go to a table. Now this is used quite a lot. For example, the size of these doors, the reason they're standardized is that they want to make sure that over 95% of people can walk through without bumping their head. They use normal distribution for that. The height of this table, same reason. This is used over and over again to make sure that you're not bumping into things along the way. That things are tall enough for you or wide enough for you. Without, of course, wasting space. Because if I make that bigger, I have to change the support in the walls and everything else. So engineers use normal distribution quite a lot. Okay, so here are the steps that we're going to use in order to do this. First, we got to convert the x into a z. Alright, so we take the 20, subtract off the mean, divide through by the standard deviation. That gives us this value, this 0.83. The way you should interpret this value, it says that this 20 is 0.83 standard deviations away from the mean. And that's your distance from the mean. 0.83 standard deviations away from the mean. The next thing we want to do is we want to find the area under the standard normal curve to the left of 0.83. So visually, here's our standard normal with its mean in the center. At 0, here's our 0.83 for our z-score. Z's are going across the bottom here. And we want to know, first, what is the probability of this, so that we can take 1 minus that and find the probability of this. So how do we do this? You have a table. This is in your ebook. This is in most standard physics books. You can just flip to the back and it's there. And this is on your formula sheet. You're going to have a z table, or going down the first column are the different values of the z, usually to the hundredths place. Going across the top, usually tenths place. Going across the top, you have the hundredths place. And what you need to do is you need to find your z value. So in our case, it was 0.83. You'd have to come down to 0.8 for the tenths place, come across to 0.3 for the hundredths place, and then we see a number in here. Now, this number in here tells us what is the probability of being equal to 0.83 or less than that, including all the way down to minus infinity. So this is saying that 79.67% of the data falls below that value. So everything back here, 6, what did I say, 7? That's the likelihood of being anywhere from here all the way down to negative infinity. So then what's the likelihood of a run out?
20.33.
23.3. Just take 1 minus that value, and we know that there's a 20% chance that given that distribution, you're going to run out of this particular oil. So when would you use this in business? Let's say you have an online store, and you need to make sure you have enough inventory going. Right? You have history of sales data. You know when your peak times are and when your low times are. When do you reorder? And how much risk are you willing to take in order to reorder? One of the problems you have when you're opening a business is that you might not know what your demand is. Anyone drink beer here? No? So there's a brewing company that was opened up by U of L students called Great Club Brewery. It's down on Bardstown Road near the Douglas Loop. The first week they opened up, they priced at $4 a glass for their particular brews of beer, which I thought was too low. And I was right, because they ran out of beer fairly quickly after opening up, which is bad, because that means there's a lot of folks who showed up disappointed and might not want to come back, because they don't know if you're going to have enough beer left over. that's something that they should have taken into account. What is the likelihood of the number of people showing up on that first day to have enough beer set aside? Yesterday, they gave out a bunch of free pizza at this new pizzeria called Blaze. I forget where it is exactly, but they did not run out of pizza. Right? They came prepared. They knew how much they need to have on stock because they saw what other grand openings looked like, and they took into account the number of people who would show up. One of the things that was always useful to me as a student was to draw out this bell curve every time, so I knew exactly the interval that I was talking about. One of the problems that you're going to find outside of this class, because inside the class everything should be consistent, but outside this class, is that this table sometimes is for the full normal distribution, and sometimes it's only for half of it. Meaning that the highest value is going to be that 0.5. You're going to have to know when to add 0.5 to your values and when to subtract 0.5 from your values in order to get the right answer. In our case, you're going to have this table, so you're always going to be able to either subtract 1 or not. It should be more intuitive in these cases. But there are other tables that exist out there that say they're z-tables, and their highest value only goes to 0.5. Right? You need to be aware of that, because if not, you're going to come to the wrong conclusion. So I would suggest, whenever you write out these problems, just very quickly, take a quick little bell curve, and highlight the area that you need to find. So you know what you're looking at and how much probability is going to be there. Alright, so if the manager of Pet Zone wants the probability of a stock out during the replenish lead time to be no more than 0.05, what should the reorder point be? Now in this case, I'm giving you a probability. Right? I'm giving you a probability, and I want you to give me an x. So we're starting at 0.05. I only want a 5% chance. If I only want a 5% chance, I got to go back to the table again. And I need to find the z associated with only 5% left in the table. Right? So in our table, that's not going to be 5%, but rather 95%. Right? So we have to go inside of the table and look for 0.95. If we do that, we find that it falls in between two values. So we're going to round this to 1.645. That gives us the z value. We know that the z from this formula is going to be 1.645. Now we know what mu is. We were told that mu was 15. Right? And we know what the standard deviation is. We're told that was 6. So we can solve for x now. To find the level of petroleum we need, oil we need in order to avoid having a runout, or at least having only a 5% chance of a runout, rather than the 20% chance we previously had with the 20 gallons. So in order to do that, you're going to multiply both sides by 6, so 1.645 times 6, and then you're going to add mu to both sides. So we're going to add that 15 to 1.645, and it turns out we need roughly 25 gallons in order to make sure there's only a 5% chance that we run out. So that's how they figured out the height of this door. They went ahead and they took the distribution of heights of people that exist in that particular country. So if you go to other countries, the heights of the door may be different. And they figured out what is the likelihood that 95% of people were able to walk through that door just fine. So they had to find what is the z-score in order to do that, and then they backed it out. And then that became the standard. Right? If you go into really old buildings, you'll notice that the heights of doors tend to be lower. Yes.
I'm going to go to this. Was that 1.6 you had on the, I think it was the previous slide? How are you getting the 1.6? I get the 0.4.
So first I need to find the 0.95, right? That's going to fall in between these two values. So the lower value is 1.64, and the upper value is 1.65.
Okay.
Averaging the two to get 1.645.
Okay, so you're just looking up the percentage within there and then looking at the
Right.
Okay.
Right? Now, Excel can look in between here. Right? And your computers, all your computers can do much finer versions of Z than we can. But that's only a recent phenomenon, actually. Right? This is something that only has been possible in, say, the last 20 years. So before that, they really had to go to tables. and go do this because it would take an IBM computer about a week to process that whole table. Now, your phone could probably do it in a couple of seconds. All right. So once we do that, we know that once you're at 24.87, there's only a 5% chance of running out of oil. So this is a useful measure. You can use this, and they do use this. Amazon uses this all the time. They use it to make sure that their prices are competitive when they have inventory, and then they make their prices non-competitive when they don't have inventory, so that you don't feel bad when they deliver 4 weeks late. Right? They try to discourage you from buying from them by increasing the price. All right, so by raising the reorder point to 20 gallons from 25 gallons on hand, the probability of the stockout decreases from 20% to just 5%. And because it's normally distributed, you notice that we only had to move a little bit to get that really big return on probability, right? Remember, one standard deviation is 6. We move less than a standard deviation, going from 20 to 24, in order to get it down to 5%. So here's your practice problem. You are designing a building. In this building, you need to create doorways. Suppose male height follows a normal distribution with the mean equal to 70 inches and the standard deviation equal to 3 inches. Find the height of the door such that 99% of men can walk through the door without bumping their heads. Now remember back to the empirical rule. Going back to the empirical rule, how big does it have to be in order to get to 99%? Almost 3, right? So use that number for right now. I'll give you the exact number on the next slide. Use that number for right now, 3. If you have the table, you get the exact number, but if you don't, just use 3 for right now. What do we got? Got an answer yet?
77 inches.
It's pretty close. So we need 99%. Which is essentially 2.33. Okay. If you used 3, then you should have gotten 79 inches. If you try to get the exact one, you're going to use 2.33. If you set this equal to 2.33, so that the standard deviation is 3, and that mean is 70, and you're solving for x. So you multiply both sides by 3. And then you add 70 to both sides. 70.
6.99.
Yeah, 76.99. So 77 inches. Okay, so what is the relationship between the binomial and the normal distribution? If you were to take the binomial and make n really large, it actually approaches a normal distribution. It gets really close to a normal distribution. So here we're going to say let the number of trials, again, still be n, but let it be really, really big. And we're going to find that the binomial gets really, really close to having a mean that's n times p, just like in a normal distribution, and having a variance that's n times 1 minus p. The binomial can be approximated by the normal distribution for very large samples. So instead of doing it that way, we can actually just calculate the z-score at 55 and calculate the z-score at 200. Go into the table, find what the probabilities are, and take the difference. And that's going to be a really, really good guess. Not exact, but a really, really good guess to what the binomial would tell us. So here we have a sample of 100 invoices, and we want to compute the probability that 12 of those are going to contain errors. So what we do is we convert that into a normal distribution. So the first thing we need is what is the mean and what is the standard deviation, because that's how we constitute our normal distributions, right? So we're going to take n, which is 100, times the likelihood of an event, which is our 10%. And that gives us 10, so that's our new mu. And then we need to find the standard deviation. That's just the formula we had before. So you're going to have that 10 times 1 minus p in there. Take the square root of that, you get 3. And now we can use those two values to approximate the likelihood of getting these 12 successes. Alright, so we want to know that area. Now, why am I doing it like this, 11.5 and 12.5? Why not just 12?
No, you can't do a 5 point.
Alright, I can't do 1 point. Can't do 1 point. So I'm going to have to give some little wiggle room in there. This is the best I can do for that wiggle room. I can't do 1 point. The reason it's not going to be perfect is because of the slope. Right? Clearly I have a little bit more weight up here and a little less weight down here. But that's why it's an approximation instead of being exact. So, the way I do that is I go ahead and find what's the probability of x being less than 12.5, just like we did before in the tables. The way we do that is we convert this 12.5 into a z-score. We take that z-score, we go to the table, and we actually already did this problem, so that 0.7967 should be familiar to you. And then we got to find the lower bound. So do it again. But this time we do it for being less than 11.5. And again, we find a z-score for that. We go to the table. From the table, we get our probability. And that gives us the lower bound of being the x. Now we need to take the difference between the two. So we're going to take that 0.7965, subtract it by this 0.6915, and that'll give us the area in between, which turns out to be approximately 10%. Now, you could go ahead and check this in the computer. Don't do it by hand. But in a computer, you can go ahead and put in 100 trials. You can go ahead and put in that you have 12 errors and find the exact probability. Itself will do that for you. You can see how close we are. All right. I have like 3 minutes left. I'll introduce this, but I'll start with this tomorrow as well, just so you kind of get it twice. The exponential distribution is a distribution we use for time to an event. This is used a lot by actuaries. You know what actuaries are? So there are people who are really good at statistics and have a very depressing job, because their job is to determine when you're going to die, when you're going to get into an accident, when is your house going to catch on fire. Right? Given different characteristics about yourself, they're looking for when bad things happen to you. They're like the bad part of a prognosticator, of someone trying to tell you your fortune, right? They're bad fortune tellers. They only tell you when not fortune is going to happen, but when dismay is going to happen. And they're really good at it, which is the bad part. Right? So they use these types of distributions to figure out that the time to an event. How quickly will you catch a particular disease, given certain characteristics about you? How quickly will you get into a car accident? Hopefully we can do some positive events, like how quickly will you graduate? How quickly will you pay off your loans? Things like that. We can do those events as well. The exponential distribution does that. It's different from the Poisson. The Poisson tells you how many occurrences happen within a set amount of time. Right? This says not quite the opposite, but almost there, right? How long to that event? That's what the exponential is telling you. How long to that event? Okay, so the exponential distribution is one where it's time to an event. So how long will it take you to graduate? How long will it take you to pay off the house? How long will it take you to pass away, to have your first child, to buy your first car? It's always time to one event. So we use this to talk about time. That's going to be very important for you whenever you're looking at questions. And the moment you hear time in a question, we're usually only talking about two distributions. One is Poisson, and one is exponential. If it's time to an event, it's exponential. And also if it's continuous, it's probably going to be exponential. And if it's the number of occurrences within a fixed amount of time, it's Poisson. And again, if it's discrete, it's going to be Poisson. So the exponential random variable can be used to describe time between vehicles arriving at toll booths, time required to complete a questionnaire, distances between major defects in a highway, how often you think a particular machine is going to break down. All those are going to be types of exponential distributions. They use this in queuing theory, so if you go into management or logistics and marketing, they want to know how quickly can you get your customers through the checkout line, how quickly can you get packages to go across the conveyor belt. One of the things that Walmart is really good at is distribution. That's why they were able to get down to hurricane areas faster than the U.S. government could. Right? UPS has been known to be really efficient about how they use their gasoline. In most cases, whenever possible, UPS trucks only make right-hand turns rather than wasting time to make a left-hand turn. Usually because they have to make deliveries along the way anyway, so they can make that same left by making 3 rights. Right? So a property of the exponential distribution is that the mean and the standard deviation are equal. Right? But this is one odd component. So if I tell you what the mean is, you automatically know what the standard deviation is. Right? It is exactly equal to. It's not like a function of. It is exactly equal to the mean. So what that means is that if your average is really high, it also means you have a lot of variance. And if your average is really low, you have a little bit of variance. The exponential distribution is skewed to the right. Its skewness measure is constant at 2. So it's not going to look like your normal distribution at all. You're not going to get that bell-shaped curve. It's not going to be symmetric in any way. This is the probability density function for it. Again, because we're talking about a continuous random variable, you're not going to use this function directly. You can plug in a number into this function, and it'll spit a number back out, but that number for you will be meaningless. Because the probability of an exact point is what again?
0.
0. Alright? However, we can integrate this thing. Alright, so we can take the integral of this thing from its lowest point, which is 0, all the way up to a upper bound, which we're going to call x for right now. And that, from there, we can actually make a new function called the cumulative density function. And unlike normal distribution, that one does have a nice closed form solution to it. So we don't have to go to a table. We don't have to go to some z table and look up the value. We can actually calculate it ourselves for any value of x. So we don't have to worry about transformations here. We can just plug and chug. So some properties about this particular distribution. If x is exactly equal to 0, right? If x is exactly equal to 0, what is the probability equal to?
0?
Yeah. No, you're right. 0, all right? If x is 0, it makes this whole exponent 0, which forces this to be equal to 1. And we get 1 minus 1, so we get 0. If x is some huge number, right? Infinity, what does this equal? It goes to 0. All right? And the reason it goes to 0 is that whenever we have a negative in the exponent, it's as if we're really talking about a fraction. Right? So, for example, 2 to the negative 1 is really 1/2. Right? So, once we have that negative in there, and we make it, say, 2 to the negative x, we're really doing 1 over 2x. What happens as x goes to infinity? This whole thing goes to 0, right?
Wouldn't it be 1 minus that small number, though?
It would be 1 minus a tiny number, but that tiny number is basically 0.
Mm-hmm.
Right?
Okay.
So that ends up equaling 1. So the bounds on time here are between 0 and positive infinity. Hopefully that makes sense to you, right? We don't have anything about negative time. If you do, use your time travel machine and fix your past mistakes. Right? So all time between arrivals of cars at Al's full service gas pump follows an exponential probability distribution with a mean time between arrivals of 3 minutes. So here our mu is 3 minutes. It also means that our standard deviation is 3 minutes. Al would like to know the probability that the time between 2 successive arrivals will be 2 minutes or less. So this is what our probability density function looks like. The interval of that tells us the area underneath the curve. So that's that cumulative density function that we have. You can see that this is not normal, right? And you can see that it is skewed to the right. Again, tiny part is where we talk about skew. So what we want to know is, what is the likelihood that after one person leaves, the next person is going to arrive in 2 minutes? That's what we want to know. So a car comes up, and they take off. What is likely another car is going to show up in 2 minutes? In order to do that, we just have to put it into our cumulative density function. So there's that 1 we were having before, minus, this is E here. This is your exponential. And then in the exponent, you have negative 2 divided by 3. All right, 2 here is your x. So this is those 2 minutes. And 3 here is your mean. After that, you're just plugging it in. So you're going to get 1 minus 0.5134, and you subtract that, and you get 0.486. So make sure we understand what's going on. We're going to use that same 3-minute mu, and I want you to tell me what is the likelihood that a car will arrive between 6 minutes and 4 minutes. I notice I gave you 2 bounds now. Between 6 minutes and 4 minutes.
0.1281.
So far, you should see a pattern, right? With the normal distribution, with the uniform distribution, with the exponential distribution. Whenever we want to find an interval, we're taking the cumulative function and subtracting off the 2 endpoints. Okay, so the relationship between the exponential and the Poisson. Poisson distribution provides an appropriate description of the number of occurrences per interval, whereas the exponential distribution provides an appropriate description of the length of intervals between occurrences.